In this session, I'll be explaining to you the time domain behavior from pole zero plot. From the above sessions, from the earlier sessions, you know what a pole zero plot is. So here we are going to study how we can determine the time domain behavior from the pole zero plot. You know that f of s is equal to h into s minus z1 into s minus z2 etc. up to s minus zn divided by s minus p1 into s minus p2 etc. up to s minus pn. The poles of this function determine the time domain behavior of the function f of t. The function f of t can be determined from poles, zeros and scale factor. That is, if we know the scale factor, zeros and poles, we will get f of s, and if we take the inverse Laplace transform of this f of s, we can get the f of t. That is the meaning of this sentence. That is, the function f of t can be determined from the poles, zeros and scale factor. And this line indicates that the poles of this function determine the time domain behavior of the f of t. That is, the time domain behavior of this function, the function f of t, the time domain behavior can be determined from the poles of the function. With respect to location of poles, the f of t can be classified as case 1, when the pole is at origin. This is the S-plane, sigma j omega. Case 1, that is when the pole is at the origin, that is pole is at 0. The f of t will be a steady state response. That is, f of t will be u of t. That is a steady state response. That is, when the pole is at origin, the f of t will be a steady state response. The second case, when the pole lies in the left half of the S-plane. How can we represent when the pole lies on the left half of the S-plane on the real axis? Left half of the S-plane on the real axis. The f of t will be an exponentially decreasing function. The response decreases exponentially when the pole lies on the real axis on the left side of the S-plane. Case 3, when the pole lies on the right half of the S-plane on the real axis. Right half of the S-plane. See, the pole is on the right half of the S-plane, then the f of t will be an increasing exponential response. To have an increasing exponential response f of t. Here we can see that the response is unbound or unstable. Unbound means, bounded means which has a limit. Here there is no limit. It's going on increasing and increasing. This is called unbounded. Okay. So when the pole is on the right half of the S-plane, the f of t, the response is unbounded and it's an exponentially increasing function. Next case, for s is equal to 0 plus j omega. That is, when the s is imaginary. These two cases were when s was real. Now the case when s is imaginary. The response f of t is equal to a e raised to plus or minus j omega n t. Here it's omega n. A into e raised to plus or minus j omega n t. That is a into cos omega n t plus or minus sin j omega n t. The e raised to plus or minus j omega n t is interpreted as a rotating phasor of unit length. Interpreted as a rotating phasor of unit length. E raised to j omega n t indicates a counterclockwise rotation. E raised to minus j omega n t indicates a clockwise rotation. So, e raised to plus or minus j omega n t will indicate a sinusoidal steady state. That is, e raised to plus or minus j omega n t indicates a sinusoidal steady state. This is the sinusoidal steady state. E raised to plus j omega n t indicates a counterclockwise rotation, and e raised to minus j omega n t indicates a clockwise rotation. Thereby, this pole indicates a sinusoidal steady state. Therefore, for s is equal to when S is on the imaginary axis. That is, here we can represent it like this. When the S is on the imaginary axis, the f of t will be like this. This is the S plane and this is the f of t. Okay, time domain behavior. When S is on the imaginary axis, the time domain behavior will be a sinusoidal steady state. Next case, when S is complex, that is sigma plus j omega n, then the f of t will be like a e raised to st. A e raised to st can be expanded as a into e raised to sigma plus j omega n t. Okay, where we can write this as is equal to a into e raised to sigma t into e raised to j omega n t. Here we can represent it like this: sigma j omega. For such a function, e raised to sigma nt. Here sigma is negative. Then we have a exponentially, sorry, not exponentially, overdamped function. We have got an overdamped function. That is, since e raised to sigma t will be a decreasing function, exponentially decreasing function when sigma is negative. Okay. Again, when we have it on the right side, that is sigma is positive, we have a underdamped function. That is e raised to minus sigma t is an exponentially decreasing function, and e raised to plus sigma t is an exponentially increasing function. So when it comes to a into e raised to minus sigma t into e raised to j omega nt, we will have this. And when we have e raised to sigma t into e raised to j and omega t, we will have this. Okay, this is an this is an overdamped sinusoid, and this is an underdamped sinusoid. You know that S is equal to sigma plus j omega. So in the plane sigma j omega plane, the real part of S, that is sigma, is the displacement from the imaginary axis, right? Sigma is the displacement from the imaginary axis. So we have a pole at a distance x from the imaginary axis. This is the real part. That is, the real part of S is the displacement of the pole from the imaginary axis, that is sigma. Sigma is also the damping factor. Greater the value of sigma, that is, greater the displacement of the pole from the imaginary axis, it means that the response decays more rapidly with time. That is, say example, we have two poles. The displacement of this pole is greater than this pole. So as the displacement increases, the response decays more fast. Here we have a response. Here we have another decaying response. So this response is much faster. This function decays much faster with respect to time. This will be given by this pole. Okay, and this indicates the decay of this pole. That is, as the distance of the pole from the imaginary axis increases, the response decays much faster with respect to time. This is the sixth property. That is, as sigma increases, that is, as the damping factor increases, the response decays much faster with respect to time. This is the sixth property. Next, here we have two sets of poles. That is, these two are conjugate pairs and these two are another conjugate pairs. Here, the property says that as the distance from the real axis increases, the frequency of the wave increases. Okay, we can represent it like this. The time domain frequency increased frequency. This is a reduced frequency. That is, as the displacement from the real axis increases, this set of pole has more displacement from the real axis. This is the real axis. This will indicate a higher frequency. This will be represented by this response, and this, as the distance from the real axis is less, to have a reduced frequency. This indicates this graph, and as the distance increases from the real axis, it will have an increased frequency. So these two come under the sixth property. So you have to by heart these 6 properties of S domain, relation between S domain and its response. You have to by heart it. Now we will just compare it with the Laplace transform we have studied. Okay, u of t, this is the function u of t. What is the Laplace transform of u of t? It's 1 by s. Here we can see that the pole is 0. See, the pole is at the origin. When we compare the pole, s is equal to 0. This is the pole and there are no zeros. Okay, this we can say that this is the function of e raised to minus at. Okay, so what is the Laplace transform of e raised to minus at? 1 by s plus a. See, what is the pole here? S is equal to minus a. See here, minus a negative sigma, a negative real value. Okay, here next we have e raised to at. This is a function e raised to at, an increasing exponential function, right? So what is the Laplace transform? In frequency domain, you will get it as 1 by s minus a. That is, the pole is a positive, s is equal to a. So we have a positive value as pole. Next we have sine omega t. This is sine omega t. Okay. For sine omega t, in time domain, the Laplace transform will give you omega by s square plus omega square. That is, s is equal to plus or minus j omega will be the poles of this function. That is, we have here minus plus j omega and minus j omega. Next, we have s is equal to sigma plus j omega n. Here we have, in time domain, we can represent this function as e raised to minus at into sine omega t. So what is the Laplace transform of this? So we have f of s plus a. When e raised to minus at is multiplied, we have f of s plus a. So here we have f of s plus a multiplied, and we have this function. And here we have e raised to at into sine omega t. The Laplace transform is f of s minus a. And if you check, you can see the s will be like this. The frequency representation will be like this. So I told about the Laplace transform of each functions just for you to compare it with the Laplace transform in the time domain and frequency domain as we have studied it before. Here we have to study just all the 6 properties of the poles and zeros, the time domain behavior from the pole zero plot. That is, we have to learn the frequency response for each position of poles. So that's all for this session. Thank you.